Okay, so most, to compute this distribution, p theta, most modern language models use something based on the transformer architecture. Now, the transformer architecture was I guess, initially invented by Vaswani et al. In 2017. So all things considered, it's relatively recent. And what it is a very specific form of a neural network that's become incredibly useful, practically useful for natural language processing. And the reason that it's sort of become useful is because it's sort of represented, in my view, a change in how people designed neural networks. So at its core, the transformer is interesting because it was first designed to be incredibly parallelizable, which is to say that you can compute the probabilities, these local conditional probabilities, say these guys here, incredibly quickly. So here's sort of a sketch of what the transformer is. We take some sort of input representations, we add some sort of positional information, and then we construct a feed forward. We alternate attention and feed forward networks till we get our probabilities. So the key idea here is that for any sentence, for instance, if I want to predict the next word from after my friend was eating chocolate, so I asked him to break a blank, what I do is I take this sentence and I iteratively apply this architecture to generate contextual representations for every token in a string. Now, this is sort of interesting, where we have the relationship between sort of language, which is fundamentally discrete. And what we mean by sort of fundamentally discrete is that if you're writing language, or you consider the process of writing it, you would write down individual symbols, you'd write down words. You'd have even if you talked about characters, you'd have a finite set of characters that you'd consider in your language. Maybe every once in a while you'd add another, like if you were writing English, maybe you'd want to spell a foreign word with a non-English character, but fundamentally it's discrete. However, this language model, like this, each of these embeddings lives in some continuous space. So we're going to embed this discrete value of a token, but we're going to put it in a more continuous and squishy space. So this is relatively useful because it allows us to talk intuitively about geometric notions of language. So we can talk about interpretable notions about the distance between different tokens in context or strings, rather than resorting to something like edit distance.